Okay, so hi and welcome to my talk on graph neural networks today here at the International Summer School 2020 at the TU Dortmund University. I'm really excited to be here and I hope you're too. So my name is Matthias Fey. I'm a third year PhD student at the University of Dortmund, and if you want to reach out to me, you can do that by mail, Twitter, or GitHub. So my research interest involves basically everything around graph neural networks, which is a fairly young and active research area. So in this presentation, I will introduce you to this really exciting research field. And so my talk will basically assume no prior knowledge on graph machine learning, but you may want to have some knowledge about deep learning in general, such as what are multi-layered neural networks, what are convolutional neural networks, what is backpropagation, and how can we train neural networks from scratch. Okay, so to start my talk, let's look at the current state of the modern deep learning toolbox. And with a closer look, we will see that this toolbox is heavily designed for operating on images and sequences such as audio signals and text. So for example, images are represented as a grid and can be inputted into a convolutional neural network for tasks such as image classification. On the other hand, sequences can hold information about text or audio signals, and those can be inputted into an LSTM or transformer network. However, it is fairly unclear on how we can apply deep learning on problems that can't be modeled by a grid or a sequence. And so the main question graph neural networks are trying to solve is how we can develop neural networks that are much more broadly applicable. The good thing about that is that we have a data structure that can mostly represent everything in the world, and that is a graph. And so to recap, a graph just holds two information. So it holds the information about nodes, which may describe entities or objects in the world, and there are edges, which model the relationship between those objects. So to go beyond classic neural networks, we want to develop neural networks that can operate on those graphs. And you can also think of them as a more general class of neural networks, since we can also represent images and text as regular graphs, for example as grids or sequences. So what needs to be done and why is it challenging? Though the main challenge stems from the fact that networks are typically very complex. So for example, networks or graphs can have an arbitrary size, which means that the number of nodes and edges may vary, and they may have a highly irregular and complex topological structure. That is in high contrast to the underlying structure of images and text. In addition, there is no fixed node ordering or reference point, which basically means that our neural networks should model a permutation invariant function. So whenever we change the ordering of nodes, our model output should stay the same. And the further challenge, networks are often dynamic, meaning that the overall structure may change over time. And furthermore, graphs may have multimodal features such as different node and edge types. And for example, we can think of a graph that contains users and products and their relations. And we can have multiple relations between different node types and different features for user and products. So in this talk, I will first cover some basic concepts like what is learning on graph and what are the typical applications. And after that, you will learn about what are graph neural networks. And besides its basic formulation, you will learn more about how powerful they are in learning representations and how they allow us to extract hierarchical patterns from the graph, and how we can scale them up to operate on large graphs. In the next topic, I want to talk about the field of relational structure discovery, which covers topics such as graph completion, where we have an incomplete graph and want to find the missing links in it. And furthermore, there might be applications where you want to find out about entities and objects and their relations from scratch, and you will learn how to do so in this chapter. And last but not least, I will cover how to implement graph neural networks, which is a fairly ignored topic in the current literature. However, the implementation of graph neural networks heavily differs from classical neural networks, so it's good to know about the differences. So let's get started. Okay, to get started, we first need to understand what learning on graphs exactly means. And the basic goal of learning on graphs is to map nodes or entire graphs into an embedding space in which they can be distinguished for a given task at hand. So for example, we might have a data set of graphs and we want to classify those graphs based on some structural properties. And for this, we would first embed each graph into an embedding space, and we would require embeddings of graphs to be distinct if their classes do not match. So more formally, a graph can be either given by a tuple of a node set and an edge set, or by a squared adjacency matrix, A, which holds an entry of 1 if there exists a link between the respective nodes, and 0 otherwise. Furthermore, there may exist additional node and edge features, and along this talk I will refer to X as the multidimensional input node features, and to E for the multidimensional input edge features, which may be optional of course. So for graph machine learning, the most common tasks are the following. So first, we have the task of node classification, which refers to predicting a class of a certain node. So for this, we have a trained model phi, which gets as input the entire graph and the node for which we would like to generate a prediction. And this model outputs a probability distribution for this node belonging to one of the classes. The second task is called graph classification, where we want to predict a class of the entire graph. And here our model generates a probability distribution for the entire graph. And the last major task is called link prediction, which refers to predicting the existence of an unknown edge. And for this, the model phi gets as input the entire graph and the pair of nodes for which we want to predict whether there should exist an edge or not. We can also categorize a learning task to be either inductive or transductive, which is a central topic in graph machine learning. And inductive learning is the main approach when training neural networks, and it refers to having a distinct set of training and test examples. And so here the model is only allowed to observe the training data, and it uses the training data for training the model. The other approach is called transductive learning, and it is commonly used for node and link prediction tasks. So here the model is allowed to observe all data, even the data for the test nodes, but it is restricted to learn from labeled training data only. So, for example, in a node classification task, you may have a very large graph, but only a few of those nodes are labeled. And we want to predict the class of the nodes that are not labeled in the training set. And however, since we know about all the nodes, their structure and their features, we are allowed to make use of these nodes during training. And this concept is also known as semi-supervised learning. Okay, so to follow up, I just want to give you an impression on why you should learn more about graph machine learning in general and graph neural networks in particular. Though the shown figure shows the percentage of keywords found for all submitted papers of the iClear conference, which is a major deep learning conference from the past 3 years. And as you can see, graph neural networks have both the highest occurrence of keywords as well as the highest overall growth from previous years. And this indicates that graph neural networks are one of the hottest research fields in the deep learning community at the moment. And I personally think that is mainly due to 2 reasons. So first, graph neural networks are still a very young research field, and there exist endless possibilities to improve upon further results. And second, it can be used in many domains and can enhance those domains by additional relational knowledge. So for example, it can be used in computer vision to learn about scene composition, or it can be used in natural language processing by the usage of knowledge graphs. Okay, so to follow up, I would like to present you a certainly non-exhaustive list of applications on which graph neural networks can be applied. And first, of course, with the sheer amount of data in social networks, applied machine learning on those graphs is highly attractive. So one could think of use cases for recommender systems for users based on some activities of friends, or tasks such as predicting a certain friendship relation between users. Next, there is a lot of interest in applying GNNs to protein-protein interaction networks, or use them to embed whole molecules. And the task includes the prediction of a certain protein function, or predicting certain properties of a molecule, for example, if a molecule is toxic or not. And there is also interest in graph generation for molecules, for tasks such as drug discovery. Another major field is 3D shape analysis, which can also be tackled by graph neural networks that operate on 3D meshes. And you can also find graph neural networks applied in the field of human pose estimation, where graph neural networks can help to identify the relationship between human body joints. Graph neural networks can be also used for visual scene understanding, where you know about objects in a scene and want to infer their relations. For example, one could ask the question whether a person sits on top of a motorbike, and graph neural networks are a good fit to handle such questions. There's also a certain interest in applying graph neural networks in physical systems, like understanding the dynamics of objects and how they may affect each other. And last but not least, graph neural networks are also applied for tackling the task of autonomous driving, where the surrounding of a car is scanned and processed into a point cloud. And this point cloud can be used to detect cars or other persons, and graph neural networks are also a good fit for operating or segmenting point clouds. Okay, so it is important to note that learning on graphs is, of course, not a new research field. So there exists a lot of methods that were developed before the rise of graph neural networks. So, for example, there exist node embedding techniques such as node-to-vec, which is really close to the word-to-vec procedure. And these node embedding techniques have the goal to map nearby nodes to a similar embedding, and to map nodes that are far away from each other to distinct embeddings. And these node embedding techniques are usually trained by sampling random walks on the graph, and use pairs of nodes on this path as positive examples, while using randomly sampled node pairs as negative examples. There also exist graph embedding techniques in the form of graph kernels, which main goal is to define a similarity between pairs of graphs. And this similarity metric is often defined based on handcrafted features. So, for example, there exists a shortest path kernel, which basically compares the lengths of shortest paths between all pairs of nodes in the two graphs. And other ideas involve subgraph pattern matching, which may count the number of occurrences of specific patterns, for example, cliques or cycles. However, with the rise of deep learning, we move to a different approach for machine learning in general. And in my opinion, this mostly stems from the following facts. So first, feature engineering or feature extraction is a hard problem in general, and it often requires domain expert knowledge. So it's also some kind of a lucky shot where you hope that your extracted features have some kind of deeper meaning for the actual task. In contrast, deep learning methods learn those features, and they do so in a hierarchical and end-to-end fashion. Furthermore, deep learning techniques have been shown to be very scalable when operating on huge amounts of data, and they are one of the approaches that best can make use of those large amounts of data. And you can verify that by the fact that we are already above human level performance on some popular tasks such as image classification. And last but not least, deep learning techniques allow the right amount of flexibility. And what I mean by that is that deep learning architectures have more and more evolved to some kind of differentiable programming where you can train sophisticated algorithms as long as they are differentiable. And this allows you to inject certain inductive biases into the model, which helps the overall model performance. Okay, so to recap, I shortly want to talk about multilayer perceptrons and GNNs, but I guess most of you will be familiar with those topics. So MLPs, or fully connected neural networks, group neurons into layers, and each value of a neuron is defined by a transformation based on all previous features from the previous layer. And this way, an MLP basically learns hidden intermediate features that are useful for the given task. And convolutional neural networks are an extension to this idea. So, and the extension is that they inject an inductive bias into the architecture, which is called translation invariance. So GNNs operate on images or sequences by sliding a window over the input, and by transforming features based on the pixels that are inside this window. And this way, the learned features are both local and hierarchical. And as we go deeper, we learn more and more deeper features or global features. And one of the advantages of GNNs over MLPs is that their model parameters are shared. So we get translation invariance and more general models due to a fewer number of parameters. Okay, so graph neural networks borrow these ideas and generalize them to graphs. So, for example, in graph neural networks, the concept of locality is a central topic. And in general, we want to learn local patterns of the graph. And while we go deeper, we want to extract more and more global information. And second, we want these learned local patterns to be universally applicable. by the concept of weight sharing, so that learned patterns are generalizable to empty nodes or graphs. This leads us to the following basic formulation for graph neural network, which is in fact heavily inspired by the concepts of convolution. And so in this talk I will define graph neural networks as following. So a graph neural network learns or updates its node representations by repeatedly transforming and aggregating node representations from the neighbors. So it's in fact really similar to a CNN, which does so for neighboring pixels. So let us describe this procedure a bit more formally, and we can do so by the concept of message passing. The message passing scheme refers to exchanging messages and updating node representations based on these messages. So first, each neighbor, and this neighbor is the node W, sends a message to its central node. So here in this case it's node V. And it sends this message along its edge. So this message might be based on the target and source node representation HV and HW in layer L-1. Next, these messages are aggregated across all neighbors. And here it is important to note that this aggregate function is typically modeled as a permutation invariant function, meaning that its output should not depend on the ordering of nodes. And typical examples for permutation invariant aggregations are sum, mean, or max aggregation. And last, the output of the aggregate function is used to update the hidden node representation of a node from the previous layer. So there are a lot of graph neural network operators proposed in literature, but they basically all follow this simple message passing scheme that is presented here. And their only difference is that they have different implementations for the functions message, aggregate, and update. So for learning meaningful patterns in the graph, the message passing functions need to be trainable and differentiable. But it's important to note that each node uses the same function for updating its node representations, meaning that the set of parameters is shared across all nodes. And in the graph neural network, these message passing operators are typically stacked and enhanced by nonlinear activation functions, just like in a traditional CNN. So, for example, given an input graph, we apply message passing phase to enrich the feature representation of each node by its neighbors, based on their input node features X, followed by an activation function. And now in layer 1, each node holds the information about the node itself, plus the aggregated information of their direct neighbors. So in the second layer, or in the second round of message passing, we again pass messages to neighboring nodes and aggregate them, meaning that each node now contains information about itself and its two-hop neighbors. And doing that so on and so forth, a node has aggregated its L-hop neighborhood information after exactly L layers. And we can use this node representation for a downstream task. So, for example, we can use the final hidden representation for the downstream tasks of node and graph classification as well as link prediction. So for node classification, we can use a classifier such as an MLP on top of each node embedding. For graph classification, we need to somehow aggregate each node embedding into a global graph representation, which is commonly referred to as a readout function. And there are multiple ways to do this, and by far the most common one is to simply add each node embedding up before inputting it into a final classifier. For link prediction, we can use pairs of node embeddings to predict the existence of an edge. So, for example, we can concatenate node embeddings before inputting them into a classifier. However, it is important to note that the training of node embeddings happens in an end-to-end fashion in conjunction with the final classifier. And this way, node embeddings can search for features in the neighborhood around each node. And it can look for features that might be relevant for the specific task at hand. Okay, so let us now look into specific implementations of this message passing scheme. And by far the most popular implementation is the following formula, which can be in fact found in numerous papers with only slight variations. And this formula updates the node embedding of a node V in layer L based on its representation itself, so that would be HV in layer L-1, and it updates the node representation based on all neighboring node representations HW. And typically, neighboring node features are first normalized before they are aggregated together. So here we have a normalization coefficient C depending on which node we want to send and aggregate information. And the aggregate function is here modeled as a sum aggregation. And afterwards, the aggregated output is transformed based on the learnable weight matrix W2 and is combined with the transformed central node information, and this is modeled as a simple skip connection. And finally, the output is sent through a nonlinear activation function to learn complex nonlinear functions. So this formulation is indeed follows the message passing scheme presented earlier. So it sends normalized node representations as messages, it aggregates them, and finally it updates the central node by the usage of skip connections and transformations. And as I said earlier, this is the most commonly found formula for GNNs, and there only exist minor differences based on the normalization coefficient C. And this normalization can be either static, so that means that C is always equal 1. But it can also be structure dependent. For example, it normalizes the neighboring node features based on the node degree. And furthermore, it can also be data dependent, meaning that the normalization coefficients are learned in an end-to-end fashion in conjunction with the node embeddings. And this is usually framed as attention, meaning that a node can attend to a neighboring node that may have the highest amount of valuable information. Okay, so there are of course other message passing operators which try to solve some of the weaknesses of the previous implementation. So, and it addresses that as follows. So first, the previous formulation models an isotropic transformation, meaning that all the nodes were transformed based on the same signal weight matrix. So looking at GNNs, this is rather unusual, since we typically have different weight matrices depending on where the pixels are in the window. So for example, in the top right corner or in the bottom right corner. And to model such anisotropic transformation, we can for example use a transformation based on an MLP, which takes in the central node representations and the difference between the central and neighboring node representations. So this way, all the nodes still use the same message passing formulation, but they get transformed differently depending on which source and target node representations are currently present. Another formulation may allow for learning on graphs with distinct edge types. So we may have a graph which can contain multiple edge types. So and the procedure for that is that we use different weight matrices depending on the edge type between node V and node W. For graphs for which we have rich edge features, we may want to transform neighboring node features based on their specific edge features, which is here modeled by a transformation function, a gamma, which takes in the edge features and transforms the node representations that way. So as you can see, there exists a variety of GNN operators that allow for operating on all kinds of graphs. And what operator is the most suitable certainly depends on the input. So as a rule of thumb, it's always a good idea to use all information that exists in the graph. So if there exist multiple edge types or rich edge features, one should incorporate them into the message passing scheme. Okay, so to conclude this first chapter about learning in graphs and graph neural networks, I would like you to answer the following questions, so feel free to pause this video to answer them. So the first question is, if you have two graphs, and for each graph you have some labeled training nodes, what would you apply here? Is it inductive learning or transductive learning? The second question is, given a social network graph with nodes being users and edges describing friendship, and you want to predict whether two users may like each other, which task maybe best describes this problem? Is it node classification, graph classification, or link prediction? And the third question is, why does the L-layer GNN aggregate the L-hop neighborhood information around each node? Okay, so in the following chapters, I wanted to introduce you to some more advanced topics regarding graph neural networks. And we'll start to do so by looking into how powerful GNNs are in learning representations. So for this, we first need to take a look into how we can define the expressivity of a graph neural network. And this is typically done by looking at their power in distinguishing between certain graph structures. So what that means is that we want our graph neural network to be as expressive as it can be in distinguishing graphs that have a different topological structure. So for this, we would like our GNN to map isomorphic graphs to the same representation, and it should try to map non-isomorphic graphs to different representation as best as it can. And to recap, two graphs are isomorphic if they are topological identically, which basically means that there exists a permutation matrix for which the adjacency matrices are identical. And we can clearly see in the figure at the bottom that the two graphs presented here are non-isomorphic, since they are topologically different. So for understanding the expressivity of a GNN, we can relate it to the WL test, which is a powerful graph isomorphism heuristic based on an iterative color refinement procedure. So the WL test can approximate if two graphs are isomorphic based on the following simple procedure. It first assigns each node a color, and for initialization, all nodes should have the same color. In the figure below, this is indicated by the color gray, which is assigned to all nodes. It then applies the following two steps iteratively. It aggregates colors from neighboring nodes, and it hashes those colors into a unique new coloring. You can see how the colors behave in the figure below. We have now 3 colors present in the graphs: orange, green, and red. And the node is assigned the color orange if it has 1 gray neighbor, and it is assigned the color red if it has 2 gray neighbors, and it is assigned the color green if it has 3 gray neighbors. So one can apply this iterative color refinement procedure for a number of steps, named L, and the WL test can approximate whether 2 graphs are non-isomorphic by looking at the color histograms obtained after the last step. So in this example, it can be clearly seen that the WL test decides that the graphs are non-isomorphic, since, for example, the left graph has 2 green nodes, while the right graph has only 1 green node, so they clearly differ. As you might see, the WL test is quite similar to the message passing or neighbor aggregation scheme applied in GNNs. So it gets passed colors or node representations from the neighbors and aggregates those node representations into unique new node representations. Based on that, one can show the following. So first, as long as a GNN is permutation invariant, it will map isomorphic graphs to the same representation. I think that is pretty clear, since the only difference between isomorphic graphs may be their ordering of nodes. And second, the power of the WL test is an upper bound for the expressive power of GNNs, which means that a GNN can never decide if 2 graphs are non-isomorphic if the WL test itself is unable to do so. It gets more interesting by looking at the third point, which says that a GNN can be as powerful as the WL test in distinguishing graph structures, but only if their aggregation scheme is injective. And this can be actually seen quite easily. So as long as we have an injective aggregation procedure, different neighbor information will get mapped to different output embeddings. However, it is important to note that not every GNN is able to achieve such expressivity. And what I mean by that is that we do not want to lose out on the information from how many neighbors a node has aggregated information from. So, for maximum expressivity of a GNN, the GNN itself is required to maintain this information. And for example, a GNN can do that by summing neighboring node representations up instead of taking its mean or maximum value. Let's look at some examples to verify that. So here we have 3 examples of 2 graphs, and we want to see which aggregation function is able to distinguish the messages sent from neighbors. And in the first example, both mean and max aggregation fail, since all nodes have the same color. In the second example, mean aggregation can distinguish neighbor information, but max aggregation cannot. And in the last example, again, both mean and max aggregation fail. However, sum or adder aggregation succeeds in all these cases to distinguish these structures. So, to conclude on the expressivity of GNNs, it is important to note that the WL test is indeed quite powerful, but since it is a heuristic, it cannot distinguish all graphs. So, for example, consider the blue and the green graph on the right. And since all nodes have exactly 2 outgoing edges and they share the same number of nodes, the WL test will fail to distinguish between those graph structures, since in each round all the neighbors will get the same color. And as a result, there is a huge interest in more expressive GNNs. And if you're interested in how one can achieve that, please feel free to check out the papers at the bottom. An important advantage of GNNs over an arbitrary hashing function used in the WL test, or its kernel variant, is that a GNN is able to learn a meaningful injectivity. And what I mean by that is that a GNN can learn how to map nearly identical graphs close to each other in the embedding space, and it can do so while still being injective. And third, although expressive GNNs are indeed an interesting idea, they are not suitable for all kinds of tasks, and there exist many domains for which less powerful GNNs that use mean or max aggregation perform better. And this can be mostly explained by the fact that graph structure discovery might be not so important for all kinds of tasks. Okay, so next I want to talk about the idea of pooling in graphs, which is in fact quite related to the concepts of pooling in CNNs. So pooling in CNNs help the model to reduce the input dimension and to widen its receptive field, and it's commonly used to obtain a global representation of an image, for example. And therefore, there is also some interest in pooling on graphs to obtain meaningful graph representations. So, in case we want to embed the entire graph, we may want to reason about hierarchies in graphs. And the potential idea is to generalize the concepts of pooling known from classical CNNs. For this, we somehow need to group nodes into meaningful clusters. And we need to pool both the graph and its node representations to obtain a coarse-grained version of it. And this is illustrated in the figure below by the colored clusters, where in each round we cluster nodes to some supernodes with which we proceed to operate. So there are multiple versions of pooling proposed in recent work, and what stands out is that it is quite hard to define the meaningful clusters of a graph in advance, since their topological structure is quite arbitrary. Instead, there has been quite a bit of interest in learning a pooling approach, which basically means that the GNN can figure out which nodes should be grouped into the same cluster. And here I want to present you two learnable pooling approaches that had the highest influence regarding pooling on graphs. And one is called dense differentiable graph pooling, which requires a GNN to operate on a dense graph, where edge weights define the probability or strength of an edge. And the second one is a variant of it which still maintains the sparsity of the underlying graph. Okay, so the idea for dense differentiable pooling is quite straightforward and uses two GNNs to learn node embeddings. One GNN is trained to learn meaningful node embeddings as before, and as we know. And the second GNN is trained in parallel to learn a cluster assignment of nodes. And as you can see at the bottom, GNN 1 computes updated node representations as before, based on the adjacency matrix A and the previous node features H in layer L-1. And what's new is the second GNN named GNN 2, which takes in once again the adjacency matrix and its node features, but this time it outputs a soft assignment matrix where values lay in the interval 0 to 1, and these values indicate the node probability of a node to belonging in one of the C clusters. pooling the graph and the node features is then rather straightforward. We can use this soft assignment matrix S to pool the graph and the node features based on matrix multiplication. However, since S is a dense assignment matrix, the resulting adjacency matrix A' is a dense one too. So, to conclude, the presented pooling approach is fully trainable, but it comes with the disadvantage that it loses out on the sparsity of the underlying graph, which is a crucial property when operating on larger graphs. Another pooling approach identifies this issue and tried to invent a learnable pooling approach that does not lose out on the sparsity of the underlying graphs. Instead of clustering nodes, here the idea is to filter unimportant nodes that might not be relevant for a given task. This filtering is based on a differentiable scoring function, which is implemented once again as a second GNN, named GNN2. So here, the second GNN, GNN2, will learn a score for each node y, and this score should be high in case the node should be kept, and it should be low in case the node should be filtered out. The pooling is then defined to only keep the nodes above a certain threshold, so for which the scores are above the threshold C, and node features are updated or multiplied by its scoring value. And as a result, the resulting adjacency matrix A is still sparse, but it does not really group or cluster nodes together, so instead it rather filters nodes out. So this still doesn't seem like the holy grail of graph pooling, and there seems to still be a lot of research interest to obtain the best of both worlds. Okay, so for the last main advanced topic regarding GNNs, I want to talk about their scalability for operating on large graphs. And as you know, graph representation learning can both be applied to a dataset of many graphs, or it can also be used in a transductive learning scenario where we want to learn from a single giant graph, and this might happen, for example, in social network analysis. So let us consider the case for now in which we want to learn on a single graph. And for this, in the past, GNNs were usually trained in full batch fashion. And that basically means that a GNN operates on the full graph, and in each layer it updates node representations for all its nodes. And this implementation has several advantages. The most crucial one is probably that it's fairly easy to implement, since we do not need to make any adjustments to the underlying computation and compute all the node updates in parallel. Another advantage is that since we know about the previous hidden representations of all the nodes, we can easily reuse them to compute the hidden representations needed in the current layer. However, this does not really scale to large graphs where we might have millions or billions of nodes, and since hidden node representations need to be kept in GPU memory, this might not fit at all. So as a result, the scalability of GNNs is one of its major research topics at the moment, and there are multiple ways to try to tackle these problems, which I will present now. So let's look at this problem in detail by considering that we want to compute the final representation of a single node, and in this case this might be node A. So by careful observation, we see that the node representation of node A defines a computation graph based on its neighborhood. So to compute the node representation of node A in layer 2, we need to compute the hidden representations of node B, C, and D in layer 1, and that again requires the input node features of node A and C for node B, of node A, B, E, F for the node C, and it requires node C and node A for computing the embedding for node D. So as one can see, to compute the final representation of a node, it requires us to compute the intermediate representations for all nodes involved in the computation graph. And that can get quite expensive really fast for GNNs with a large amount of layers or graphs with a high average node degree. So this problem is known as the neighborhood explosion problem. And since it requires us to compute d to the power of L intermediate embeddings to derive the final node representation. And here d stands for the average node degree, and L denotes the number of layers of the GNN. So one way to resolve this issue is to restrict the neighborhood size by making use of sampling techniques. So for example, in each layer and for each node, we might sample only 2 neighbors during a single forward pass. So here in this example, we sample for the final node representation for A only the neighbors C and D, and for neighbor C, we sample its neighbors E and F. So this way, we certainly restrict the neighborhood explosion problem to an upper bound of 2 to the power of L. So as a result, we are able to train shallow networks on large graphs, given that the number of layers is not too large. However, the neighborhood explosion problem still takes place as we develop deeper and deeper graph neural networks. And furthermore, it results in a complicated underlying implementation, since in each layer we need to keep track for which node we want to compute embeddings for. So as an alternative formulation regarding scalable GNNs, there exists an approach that gets completely rid of the neighborhood explosion problem, and its main idea is based on partitioning the graph into subgraphs. So for this, each obtained subgraph gets trained independently, and we can train it just like the way we would do it when we were operating on the full graph, this time just with a smaller amount of nodes. So the illustration at the bottom shows that this formulation indeed prevents neighborhood explosion. So by deleting the edge between the 2 subgraphs, a GNN that makes use of partitioning only operates in one of the subgraphs at a time. And in contrast, if we do not partition the graph, the neighborhood information gets quickly required for the other subgraph as well. So this formulation has several advantages over the previous approach. The most prominent one being that we can stack arbitrary many GNN layers without any neighborhood explosion problem. It also comes with a straightforward implementation where we just operate on one subgraph at a time. However, it is important to note that the partitioning introduces an unintended bias into how GNNs learn node representations, and that can certainly limit its expressive power. So this bias stems from the fact that if we remove some of the edges in the preprocessing step, a GNN is not able to use those edges, but those edges might be indeed important for the actual task at hand. So another approach that tries to tackle the problem of scalable GNNs is called simplifying their computation, and is based on the following observation. So in its most simple form, the computation of a GNN can be formulated as follows by a simple matrix multiplication scheme. So here we have the adjacency matrix A, which gets multiplied by the input feature matrix X. And note that this corresponds to an aggregation of neighboring node features. And afterwards, the aggregated output is transformed by a trainable weight matrix and is then passed into a nonlinearity. So in the second layer, we do this again. this time using the hidden representations of layer 1 as input for our node features. Now, what happens if we omit the nonlinearities? So as one can see, we get a simplified version of the GNN computation, where propagation can be expressed by the adjacency matrix A to the power of L, and where the multiplication of weight matrices can be expressed as a single weight matrix. And as you can see, by omitting the nonlinearities from the underlying computation, we can decouple the actual prediction from the propagation. So that means we can now pre-process the result of A to the power of L multiplied by our input features x, and simply use this representation to apply a machine learning algorithm such as logistic regression or deep neural networks. So in this way, we kind of decouple the prediction from the propagation. So now we are able to achieve very fast training on billion scale graphs by making use of mini batches and learning algorithms such as logistic regression. However, this implementation comes with a price, and by omitting the nonlinearities from the underlying computation, we certainly limit the GNN's expressivity. Okay, so to conclude, scalability of GNNs is still an active research area, and which method one wants to apply certainly depends on the task. So for shallow networks, one can make use of neighborhood sampling, while for deeper networks, partitioning might be the way to go. And simplified GNNs without nonlinearities might be the best option in case your graph is very large, since this scheme requires the least amount of time to finish training. Okay, so this ends the chapter about advanced topics regarding GNNs, and I would invite you to answering the following questions. Again, please feel free to pause this video to answer them. So, the first question of my talk is the following. Do you can think of an example in which the WL test fails to distinguish non-isomorphic graphs? The fifth question is, for which task would one want to typically apply graph pooling? Is it node classification, graph classification, or link prediction? And the sixth question is, why does the neighborhood explosion problem not occur when training a GNN in full batch fashion? Okay, so in the next few minutes I would like to address an evolving topic that can be framed as relational structure discovery, and that got recently a lot of attention from the community. So in the previous talk I made a crucial assumption, and that assumption was that we did exactly know about what the nodes and edges are in our graph. So basically, we were just given a graph and we wanted to apply some machine learning on it. However, this is not always the case, and there are basically two scenarios that are complementary to working with graph neural networks. And the first question is the following. So, what if we have incomplete knowledge about the relations in our graph? So while this can be tackled by the task of link prediction, so in case you have an incomplete graph and you want to infer the missing links, it gets a bit more interesting in case you know about the objects or nodes in the scene, but you have absolutely no clue about their relationship. And this problem is typically referred to as relational inference, where you want to infer all links completely from scratch. The second question is, what if we do not even know about the nodes? So, for example, we are given a scene that evolves over time, and we want to learn about the objects, entities, or events in this scene, and in particular how they relate to each other. So this object discovery can be also seen as a grouping or clustering of low-level features that might indicate relevant objects in the scene. Okay, to get started with this exciting topic, I would first want to recap on how we do graph completion or link prediction in GNNs. And this is basically built upon a simple recipe. So first, we apply an encoder on the incomplete graph, and this is usually modeled as a GNN. And second, we have a decoder that maps pairs of latent node embeddings to a probability. And this probability indicates the existence of an edge in the graph. Okay, so how do we train such a completion network? So of course, we cannot only train the neural network on positive edge pairs, since then our decoder would basically learn nothing. But instead, we need to train it with a contrastive loss, that is, we feed it with both positive edge pairs and negative edge pairs. And the negative edge pairs are typically just randomly sampled. It's important to understand here that we might sample positive validation and test pairs as negative ones during training, since we do not know about them during the training process. So in practice, this doesn't really make a difference, since the probability of sampling such an edge pair is rather low and shouldn't affect training all that much. So okay, now you know how to infer the missing edges of a graph, but what if we are only given nodes without any further information about their underlying edges? So for example, consider the figure on the right, where you have some objects moving around over time. And in fact, the movement of those objects may depend on each other, but we do not really know yet. So for predicting the movement of a single object, it's much more beneficial to understand the relation and movement of all these objects in the scene to make a prediction on how the objects behave in the next time step. And as I said earlier, this problem is framed neural relational inference and can be as well solved by applying GNNs and following a simple recipe. Okay, so now imagine you have some observed dynamics over time. So you have an unordered set of vectors that describe the objects at each time step, which we call Ix here. And what you can do now is you can apply a GNN on the fully connected graph, where nodes describe the objects and events in the scene. And now the GNN can learn about all the movements of objects and how they relate to each other. So the output of the GNN is an interaction graph proposal, which basically defines which objects relate to each other. And to train the neural network, you need a second GNN that is operating on this graph proposal and use it to reconstruct the dynamics of the next time frame. So while the training is based on a reconstruction loss, we are mostly interested in the output of the first GNN, which can learn about the object's interaction in a completely unsupervised fashion. The next topic I want to talk about is a case where we do not even know about the nodes or objects in our scene, and we want to infer those nodes and relations from scratch. So, for example, consider the scene of cars on the road, and we want to predict the next time step of this scene. So there are two different views to look at this problem, and they are framed as unstructured world model and structured world model. The unstructured world model is given this image and tries to encode it with no prior knowledge into an embedding from which the scene can be reconstructed. And this embedding can potentially be derived by a convolutional neural network. And we frame this learned embedding C1 here. And given an optional action and the next time frame, we want our model to predict the embedding of the next time step, which we can learn through a transition model. And this model is typically learned by decoding the embedding back into an image and comparing it based on a reconstruction loss. The structured world model assumes that our world is structured and that objects and entities are in interaction with each other. Here again we take an observation at time step t equals 1 and pass it to an encoder, which can be again a convolutional neural network. However, this representation is different since we structure it as a set of latent variables. So here we have, for example, n elements, and each element can represent a single object of the input. To derive at the next time step, we again pass the latent representation through a transition model. This translation model is special too, since it now takes as input a set of latent vectors and can model independent as well as dependent predictions of objects from other objects. Okay, so the basic architecture for training structured world model looks as follows. So here we have an observation at time step t, and we begin by extracting objects using an encoder module. And this object extractor is typically modeled as a convolutional neural network, which outputs a feature map for each object found in the observation. This feature map is further compressed by an object encoder, which maps each feature map into a low-dimensional vector Ct, resulting in a set of vectors describing objects. The transition model can now learn to model the pairwise interaction between objects using a GNN on the fully connected graph to derive at an explanation for the next time step z plus 1. Both the encoder and the transition model are trained end-to-end based on a contrastive loss given the ground truth next hidden state and the random state from the dataset. And the cool thing about this formulation is that this allows the network to be trained in a fully self-supervised fashion, which basically means that the model learns about objects and their interaction completely on its own without any further supervision. Another advantage of this model is that it can be trained directly in latent space without any decoding taking place. So this allowed the model to avoid modeling task irrelevant details. For example, for certain prediction tasks, it might not be necessary to model stuff like colors, background, or patterns of objects, and we just care about their dynamics, and this model is able to achieve that. Okay, so this concludes my introduction to the field of relational structure discovery, which I'm personally really excited about since it can have a real impact on how we model the world using deep neural networks. And again, please feel free to answer the following questions. So question number 7 asks, for the task of graph completion, what would be regarded as negative edges during training? So first, all edges that are not part of the training set. Second, all edges that are not part of the training validation set. Or third, all edges that are not part of the training, validation, and test set. And the 8th question asks the following. What is the advantage of training structured world models directly in latent space? So in the last part of my talk, I want to talk about implementing and training GNNs, which is a fairly important topic to cover in my opinion, since there are some differences one needs to be aware of in contrast to working on images and sequences. And so most of these differences stem from the fact that modern deep learning frameworks are heavily designed for operating on dense representations. So in this part, I will cover some basic topics like how can we achieve effective parallelization on irregular and sparse graphs, and how one would implement mini-batching capabilities when operating on a dataset of graphs, which all have potentially different sizes. And last, you will learn about the PyTorch Geometric library, which is an extension to PyTorch for deep learning on graphs. And PyTorch Geometric is a fairly popular library to do so, and it's developed here at the TU Dortmund University. So let's dive in. Okay, so consider that we are given a graph, and that the representation of this graph is sparse. And so this graph is defined by a node feature matrix X, which holds the node features for all the nodes in our graph. And this graph is further defined by its edge indices I, which store for each edge in the graph its source and target node index. So this edge index format has a shape of 2 times the number of edges. And furthermore, we may are given optional edge features that store a feature vector for all the edges in our graph. Okay, so to represent a graph on the left, we have a node feature matrix which contains 4 feature vectors for the nodes 1, 2, 3, and 4. And we can represent I, the edge indices, as shown below. So for example, since there exists an edge from node 2 to node 1, the edge index matrix stores the pair 2, 1 in its first row. Okay, so how do we apply a general form of message passing on this given graph representation? So one very convenient approach is to lift the node representations into an edge parallel space, on which we can compute the messages sent along each edge in parallel. And this operation is typically known as the gather operation on the GPU. So here, gather looks at the indices of source and target nodes, and lifts each node representation to an edge representation. After computing the messages sent along each edge in parallel, we need a way to convert or aggregate these messages back into the node space. And this operation is typically known as a scatter operation. So this scatter operation takes in the target node indices of an edge and uses them to aggregate the messages together that are part of the same destination. And so this scatter operation provides different reduce capabilities, and we may have the option to aggregate messages based on summation, taking the mean or taking the maximum of values. And last, we can update the node representations by implementing the update function. And as you can see, this implementation is very flexible, since it disentangles the message, aggregate, and update functions from the underlying computation. And that comes really handy when doing research on GNNs. Okay, so next I want to talk about mini-batch handling in GNNs. And so for mini-batching, there is a major difference in contrast to, for example, batching in convolutional neural networks. And to recap, in convolutional neural networks, you have a designated batch dimension, and that basically assumes or requires images to have the same input dimension. And for graphs, that is not really applicable at all, since graphs can have potentially different sizes across the dataset. So one way around this problem would be to pad the graphs with fake nodes. But this usually complicates the implementation and would result in a lot of unused fake nodes for the computation. Okay, so a better way to handle mini batches in GNNs is the following procedure. So for GNNs, we can represent the distinct graphs in a mini batch as a single giant graph with disconnected subgraphs. And the subgraphs correspond to a single example in our mini batch. And we can achieve that by stacking the adjacency matrices of the graph in a diagonal form and by concatenating node representations vertically. And so the main advantage of this scheme is that the GNN does not need to handle the different cases, whether it is trained in a mini-batch fashion or not. Since GNNs aggregate neighborhood information from their direct neighbors, there is no way that the disconnected graphs in our mini-batch can receive a message from another graph. And furthermore, there is no additional memory and computation overhead required to operate on this mini-batching procedure. So, for example, we do not need to pad the graphs to the same length, and since adjacency matrices are stored in a sparse representation, there is no additional memory required to stack them. And furthermore, this scheme naturally supports examples of different size. However, one needs to take care when applying readout functions to obtain global graph representations. Since we no longer have a distinct batch dimension, we need an additional vector which tells us which node belongs to which example graph. And this is indicated here by the assignment vector. So for applying readout functions, one would take in the output node representations in conjunction with the assignment vector to obtain a global graph representation for each graph in the mini-batch. Okay, and the same holds true when applying graph pooling. So now we want to coarsen this single giant graph, and we do not want to pool or cluster nodes of different examples together. So for applying pooling on graph, the usage of this assignment vector ensures that. Okay, so now that you know how to compute a round of message passing and how to form mini batches of a set of graphs, I want to introduce you to the PyTorch Geometric library, which is a Python library built upon the popular PyTorch deep learning framework. And it is designed to enable deep learning on graphs directly in PyTorch. So the PyTorch Geometric library comes with the following features. It simplifies implementing and working with graph neural networks by providing a simple to use message passing API. And it omits the need of rewriting common logic, and that may include GNN operators, loading and working with datasets, or taking care of the previously presented mini-batch approach. And last but not least, it bundles fast implementations from a variety of published papers into a unified framework so that it helps users to apply GNN to a specific problem where relational learning might be important. And it is particularly useful for researchers to compare themselves to related approaches and to make research overall more reproducible. Okay, so to this date, PyTorch Geometric bundles a wide range of different GNN operators that are built based on different insights and inputs. So there exist GNN operators that can operate on graphs with different edge types, and there exist operators that can make use of multidimensional edge features. PyTorch Geometric also provides a variety of pooling operators and complete models, and with some of them even being pre-trained. And furthermore, it provides a lot of useful utilities, for example, to scale GNNs up, for normalization, or to explain the output predictions made by a GNN. Okay, so let us now look at an example on how to use PyTorch Geometric in practice. So I try to present that as easy as possible, but there might be a kind of steep learning curve if you have never implemented a deep neural network in PyTorch before. Okay, so the first action is that we need to load our data into PyTorch Geometric. And luckily, PyTorch Geometric already provides most of the commonly used datasets in research, But if you want to implement your own datasets, there are a lot of utilities to help you out. Okay, so let us load a predefined PyTorch Geometric dataset. And for this we load the PPI dataset, which holds exactly 24 graphs which describe protein-protein interactions. And 20 of those graphs are typically used as training graphs. So PyTorch Geometric will automatically download the respective dataset and store them on disk, so that's really convenient. Okay, so now we can inspect this dataset, for example by printing the overall dataset description, and we can print out the first graph inside the dataset. And here we can see that the dataset indeed holds 20 training graphs, and we can see that the graph is stored in a data container, and that the information about what is present in the graph is nicely laid out to us. So we can see that the graph contains the edge index matrix, which is a matrix of shape 2 times the number of edges. And we can see that the graph comes with node feature matrix X and ground truth labels Y for each of its nodes. So here the first graph holds the information of around 1,700 nodes, and each node has a 50-dimensional node feature, and the task is how to predict the existence of around 120 labels. Okay, now we can use the data loader class to create mini batches of this dataset. So here we would create mini batches of size 2, and we want our mini batches to be created randomly by setting the shuffle option to true. Okay, so now we can inspect the first element provided by our data loader. And we can see that we no longer get a single data object back, but instead we get a batch object back. So there exists now around 3,400 nodes in our supergraph, and the number of edges is also increased. And the batch object holds a specific attribute which is named batch, which basically just models the assignment vector mentioned earlier. And this is that it holds the information which node belongs to which example. Okay, so having our data to be ready to use, we can construct a simple network architecture to learn from this dataset. And here we make use of the GNNs, which is one of the most basic and simple GNN operators in literature. Okay, so defining a network is really straightforward. We first need to initialize the GNN operators that we want to use in our network. And here the arguments passed to creating the GNNs describe the input and output feature dimensionalities of nodes. So here our first GNN operator expects as input dimensionality the number of node features in our dataset, and it will map those to a hidden dimensionality of 256. And next, we want to apply a second operator that maps this hidden dimensionality to the number of classes in our dataset. Okay, so with this, we need to define the forward computation of our model. And here we get the node feature matrix X and the edge connectivity matrix edge index as input. And we simply stack the two GNN operators to compute the output node embedding. And we decide to apply a ReLU nonlinear activation between the GNN operators. Okay, so with this, we have everything ready to train our model. So we first initialize it and send it to the GPU, and we create an optimizer that takes in the model parameters, a learning rate, and its task is to update the model parameters based on their gradients after each round of forward propagation. Okay, so training a GNN model is really similar to training any other model in PyTorch. So we iterate over our data and send it to the GPU. And next, we compute the output of the model for the specific mini-batch. We can then use this output to compute the loss based on the ground truth node labels. And we can use this loss to further compute the gradients of the model parameters and use those gradients to update them. Okay, so that is basically all it takes to implement a simple GNN from scratch. Next, let's look how one would make PyTorch Geometric scale to giant graphs. So consider the case where you have a single giant graph, and for graphs which are really big, you may encounter a runtime error saying that CUDA is out of memory. So that would here look as follows. We input our data object into the training function and want to compute the forward pass and compute the loss. But that call did not succeed since we get a runtime error. So luckily, PyTorch Geometric comes with some utilities to enable learning on those giant graphs. And here we want to make use of the partitioning approach. To recap, the partitioning approach suggests to partition the graph into multiple subgraphs, which can then be processed independently. And so for converting a giant graph into a number of partitions, all you need to do is creating a partitioning loader, which is named here cluster loader, and that will first partition or cluster the graph into a number of partitions, and then it will provide mini batches of those clusters. Okay, so the only change in our training procedure is now that we need to iterate over the loader instead of just operating on the raw data. And then we need to process the graph in mini batches. And as you can see, scaling GNNs up with PyTorch Geometric is really straightforward and only requires a few lines of code change. Okay, so to conclude, PyTorch Geometric provides uniform implementations of over 40 GNN operators and models, which might be suitable for different learning tasks. And it's also extendable by using a simple message passing interface. Overall, it provides access to over 100 benchmark datasets, and which will get downloaded automatically. It provides automatic mini-batching procedures both for operating on a dataset of graphs as well as for operating on single giant graphs. And it further provides a variety of pooling operators and readout functions. And it comes also with some useful transforms such as augmentation or point sampling. And overall, PyTorch Geometric is pretty fast, and we achieve that by making use of dedicated CUDA implementations for our GNN operators. So if you're interested in learning more about GNNs and applying it to your own problems, please feel free to check out PyTorch Geometric, which we fully open sourced on GitHub. And there's also a tutorial session here at the summer school in which you can work with PyTorch Geometric directly, so please feel free to join this session. I'm looking really forward to seeing you there. Okay, so to conclude this chapter, I would like you to answer the following questions. So again, please feel free to pause the video to answer them. So question 9 and 10 ask, what are the advantages or disadvantages of the presented mini-batching approach for GNNs? Question 11 asks, what are the time and memory complexities for executing a single round of message passing? And question 12 asks, For aggregating messages, which operation would you apply? Is it the gather operation or the scatter operation? Okay, so this finishes my talk about graph neural networks, and I hope that it was a great experience for you and that you may have taken something out of it. So in this talk you learned about graph neural networks and that they are able to learn localized node embeddings by following a simple message passing scheme, which is in fact quite similar to the one applied in convolutional neural networks. And I also presented some exciting research opportunities for GNNs, like studying their expressive power, how one could enhance them to learn hierarchical representations by the usage of pooling, and how we can scale them up to operate on really giant graphs. It's also important to understand that GNNs can help us to reason about the relational structure in our world, which is, in my opinion, one of the key steps in achieving more general AI. And furthermore, GNNs can be already applied in many domains, such as computer vision, natural language processing, biology, chemistry, or physics. Of course, my talk was just a basic introduction into the world of GNN. And in general, there are many things that I couldn't cover in this talk. And that would include topics such as temporal or dynamic GNNs, where the underlying graph structure will change over time. We didn't also cover topics such as pre-training or transfer learning of GNNs. And last but not least, we didn't cover any topics such as higher order GNNs or generative models, which are also really exciting topics in my opinion. Okay, so thanks for watching and I wish you a great day. Bye.